So today I'm taking a look at pH curves of acids and bases, and I'm going to use that taking a look at some old diploma questions like before. So to start off with, here is a question that shows a pH curve with some different parts highlighted that we have to understand. And anytime you're looking at a pH curve, you will have your pH on the y-axis, and that would be measuring out the pH of the Erlenmeyer flask. So this is my very bad Erlenmeyer flask, but essentially there would be a pH probe in here, and we would be measuring the pH as you're adding in the base. And that's what's going on the x-axis. So on the x-axis, you will always have what's in the burette, the solution of what you're adding in. So to begin with, we know what's being titrated because we see that we have a pH of 7 here, the pH of 7 is indicated. Down here it would be 0. So the fact that you're not starting close to 0, we know it's not going to be a strong acid, but it is between 0 and 7. So that means it is going to be weak. So that's our first part. And then it's titrated, it's showing us that it's titrated with a strong base. And we only know that by making this titration go further than the endpoint. So before we move on, when you're looking at a graph, the first part here where it's showing that number 2, that is showing a buffer region, but that would only exist if we have a weak substance. And because we have a weak acid, you have a buffer region. So if you don't have anything weak available, there is no buffer region, even if you can see it on your graph. Part 1 here is just that quick dip of pH before that buffer kicks in. And then you have that vertical kind of section, and that would be your equivalence point. And that's always the halfway point of this vertical line, which looks like it's slightly above 7. And based on that is how you would pick an indicator. So we would take a look at that for an indicator. Even though this question's not asking that, it could. And then lastly, knowing that this is where your titration ends, but to get that complete curve, you keep titrating until it flattens out, and that ending area would be that pH of whatever you're adding in. So going back to the question, it is asking what we're titrating with. We have that weak acid titrated with a strong base, and the buffering is occurring at only region 2. So the answer is C. So this region here, region 5, that's just the end of the titration. There is no weak acid there anymore. It is all base, so we don't have to pick that section. Moving on to this next question, and this happens a lot with pH, is just understanding how the pH shifts. So if you're going from a pH of 2 to a pH of 4, you are becoming less acidic, right? You're moving towards like the basic numbers, right? Becoming neutral and then heading into a base. So if you're going from 2 to 4, we're going to write down less acidic. So to begin with, talking about the hydronium concentration, if it's becoming less acidic, we know that it is decreasing. And every time you move on the pH scale, so if you're moving from 2 to 3, your hydronium concentration changes by a factor of 10. So this first shift from 2 to 3, you would multiply by 10. And then going from 3 to 4, you would multiply by another 10. So 10 times 10 gives you that factor of 100. And knowing about hydronium, because you're moving up the pH scale, your hydronium would be decreasing by a factor of 100. This last question is a bunch of information, and it seems like we're bringing in pH, so not necessarily about a pH curve, but it gives you this information about hydrangea flowers, talks about the reaction, and we show that the reaction's in equilibrium. You also get a Kc value. But then based on the question, it is asking you at equilibrium, compare the rate of the reverse reaction to the rate of the forward reaction. And we want to look at the pH of the solution over time. So this question seems like there could be work to it, but it is really just a theory question. And it's showing that you know the definition of equilibrium. And that is that the rate of the reverse reaction is equal to the rate of the reverse forward reaction, So we can rule out A and B. And then in regards of pH, so the fact that you have hydroxide might throw a few people off thinking if it's being produced, but this reaction is going in both directions, so it's also being used up. So with that, nothing's happening to the pH, right? Because you're in equilibrium. So if you're in equilibrium, your pH has to stay constant. So you can rule out C, and I'm not sure if you can see this on my screen here, but the answer is that it's equal and it will remain constant. So like always, if you did find this video helpful, please like and subscribe. And if you have any videos that you would like me to show, please just leave me a comment. Thank you for watching.